velocities of stars in the outer regions of the galaxy suggest the presence of a dark matter halo that extends well beyond the visible boundaries. This hidden mass exerts a gravitational influence that stabilizes the galaxy and maintains the integrity of its spiral arms. Observations of the whirlpool-like entity have significantly contributed to the broader understanding of how dark matter shapes galaxies across the cosmos. From the vivid colors of the grand spiral nexus, observed in optical and ultraviolet wavelengths, to the infrared glow of its dusty interstellar medium, every observation provides a piece of the cosmic puzzle. Astronomers have leveraged instruments such as the Hubble Space Telescope and the Very Large Array to capture high-resolution images and spectra of this galactic system. These datasets not only enhance our understanding of this particular galaxy but also serve as a comparative baseline for studying more distant systems that share similar characteristics. The stellar collision nexus remains a site of frequent supernova activity. These cataclysmic events, often occurring in the spiral arms, are observable as brief yet extraordinarily bright flashes. Each supernova provides a unique opportunity to study nucleosynthesis, the creation of heavy elements such as gold and uranium. By analyzing the light curves and spectral lines of these events, scientists unravel the complex processes that govern the life cycles of massive stars and their explosive deaths. The cosmic turbine of NGC 5194 exemplifies how interactions between galaxies fuel dynamic processes. The bridge of material linking the primary galaxy to its companion is a testament to the power of gravitational forces. This bridge, composed of stars, gas, and dust, allows for material exchange between the two galaxies, further complicating and enriching their evolution. Simulations of this interaction, conducted using advanced computational models, have allowed scientists to recreate the observed structures and dynamics, shedding light on similar processes occurring in other galactic systems. As our understanding of the intergalactic vortex deepens, it becomes increasingly clear that this galaxy is more than just a striking visual feature in the night sky. It is a cornerstone for scientific exploration, offering insights into a wide array of cosmic phenomena, from the formation of planetary systems to the large-scale structure of the universe. With each new discovery, the Whirlpool system continues to remind us of the intricate and awe-inspiring nature of the cosmos. The celestial Whirlpool pair, with its iconic sweeping arms and brilliant central hub, continues to unravel the mysteries of the universe. While its beauty has captivated stargazers for centuries, it is the depth of scientific data embedded in its structure that makes it invaluable to astrophysics. The primary galaxy, often described as the spiral dynamo of the north sky, acts as a natural laboratory for studying the forces that shape galaxies, drive star formation, and govern cosmic interactions. One of the key areas of research in this galactic wonder is the role of density waves in forming and maintaining its spiral arms. Unlike solid structures, these arms are composed of stars, gas, and dust moving in and out of gravitational traffic jams as they orbit the galactic center. These density waves compress gas clouds as they pass through, triggering waves of star formation. This self-sustaining process ensures that the whirlpool maintains its elegant spiral structure over millions of years. The ability to study this phenomenon so clearly in this system has helped astronomers understand how other grand design galaxies form and evolve. The intergalactic dance of NGC 5194 and its companion, NGC 5195, also reveals the long-term consequences of galactic mergers. Observational data shows that the smaller galaxy has already passed through the disk of the larger one multiple times, leaving behind tidal tails, arcs, and plumes of stars and gas. These remnants of gravitational interaction act as a memory of the encounter, offering a timeline of past collisions. Such detailed records are rare and provide critical evidence for understanding how galaxies like the Milky Way may have formed through similar interactions in the past. The heart of the cosmic vortex, the nucleus of NGC 5194, is not merely a quiet gathering of old stars. Instead, it is a bustling hub of activity dominated by the supermassive black hole at its center. With masses millions of times that of the Sun, this black hole exerts immense gravitational pull, drawing in surrounding gas and dust. As material spirals inward, it heats up to millions of degrees, releasing high-energy radiation that can be detected across vast cosmic distances. This phenomenon makes the nucleus of the Whirlpool an active galactic nucleus, AGN, albeit less luminous than quasars. By studying AGNs like this one, scientists gain a better understanding of the relationship between black holes and their host galaxies. The Stellar Bridge Galaxy is also a treasure trove for studying the life cycle of stars. Its spiral arms host a variety of stellar populations, from bright blue giants in their infancy to red giants nearing the end of their lives. Using spectroscopy, astronomers can determine the chemical composition of these stars and their surrounding gas. This data reveals how generations of stars have enriched the galaxy with heavier elements, a process known as chemical evolution. These elements, forged in the cores of stars and released during supernovae, are the building blocks of planets, life, and even ourselves. Moreover, the whirlpool's proximity and clarity make it an ideal target for studying the interplay between magnetic fields and star formation. The magnetic field lines, mapped using radio telescopes, align with the spiral arms, guiding the movement of charged particles and influencing the collapse of gas clouds into stars. Understanding these magnetic processes is crucial for piecing together the puzzle of star formation in galaxies across the universe. In recent years, the galactic gravitational showpiece has also become a focus for research into dark matter. The rotation curve of NGC 5194, which plots the orbital velocity of stars and gas at varying distances from the center, does not behave as expected based solely on visible matter. Instead, it suggests the presence of an unseen halo of dark matter that provides additional gravitational pull. This dark matter halo not only stabilizes the spiral structure but also plays a vital role in shaping the galaxy's overall dynamics. The whirlpool-like nexus has even contributed to the study of cosmic expansion. Using the Cepheid variable stars within its arms, astronomers have refined measurements of the Hubble constant, a key parameter that describes the rate at which the universe is expanding. By comparing these observations with those of other galaxies, researchers can test models of cosmology and explore mysteries such as dark energy. Beyond its scientific contributions, the cosmic tidal sculpture continues to inspire awe and wonder. Its breathtaking images, captured by observatories like Hubble, have been widely shared and studied, igniting public interest in astronomy and space exploration. Each image reveals new layers of complexity, from the intricate dust lanes that weave through its spiral arms to the faint tidal streams that hint at its tumultuous past. As telescopes become more advanced, the Whirlpool Galaxy and its companion will undoubtedly yield even more secrets. The upcoming generation of observatories, such as the James Webb Space Telescope, promises to peer deeper into the infrared, unveiling hidden star-forming regions and the faintest structures in the system. These discoveries will not only enhance our understanding of the Whirlpool galaxy but also provide broader insights into the processes that govern the evolution of galaxies throughout the cosmos. The Whirlpool system, with its interplay of beauty, science, and cosmic history, stands as a symbol of humanity's quest to understand the universe. Each observation, whether of its spiral arms, its active nucleus, or its gravitational interactions, brings us closer to answering the fundamental questions about our origins and the nature of the cosmos itself. Should I continue delving into more aspects or refine specific sections further? The majestic spiral of Cain's Venatici remains a cornerstone in the study of galactic morphology, providing astronomers with unparalleled insights into the forces and processes that shape galaxies. Its ability to reveal complex structures, dynamic interactions, and a range of stellar phenomena has made it a focal point for both theoretical and observational research. The Whirlpool, or stellar maelstrom, as it is sometimes called, serves as a gateway to understanding the broader mechanisms that govern cosmic evolution. One of the most striking aspects of the interstellar dynamo is the intricate balance between chaos and order. Despite the violent gravitational interactions with its companion, the spiral nexus has maintained its well-defined structure. This paradox is explained through the concept of density wave theory, where spiral arms are not static features but rather regions of higher density that move through the galaxy. This dynamic behavior allows the arms to persist even as individual stars and gas clouds move through them. The study of this mechanism has implications far beyond M51, helping astronomers decode the behavior of spiral galaxies across the universe. The galactic tidal duo offers a rare glimpse into the early stages of a galactic merger, a process that can take billions of years to complete. Simulations show that the smaller galaxy, often referred to as the stellar intruder, is gradually losing its distinct identity as it becomes engulfed by the larger whirlpool. This ongoing interaction provides a live demonstration of how galaxies grow and evolve through accretion and mergers, processes that are thought to have played a major role in the formation of massive elliptical galaxies observed today. Another remarkable feature of the celestial whirlpool pair is the bridge of material connecting NGC 5194 and its companion. This stellar and gaseous bridge is a direct result of tidal forces, where the gravitational pull of the smaller galaxy distorts the disk of the larger one. The material within this bridge includes young stars, molecular gas, and interstellar dust, all of which are subjected to intense radiation and gravitational shearing. Detailed observations of this bridge have provided critical data on how tidal interactions redistribute material within and between galaxies, fueling star formation and triggering bursts of activity. The whirlpool, often referred to as the cosmic engine, also stands out as a prolific factory for stellar creation. Infrared observations reveal the presence of dense molecular clouds within its spiral arms, where conditions are ripe for the birth of new stars. These regions, often hidden in optical wavelengths by interstellar dust, are illuminated in the infrared spectrum, offering a clearer picture of the early stages of stellar formation. The ongoing starburst activity in the whirlpool is not just a localized phenomenon but a cosmic relay, as the energy and materials produced by these stars will shape the galaxy's future. The stellar whirlpool system is also a key site for studying the end stages of stellar evolution. The supernovae observed in its arms are not isolated events but rather the natural culmination of a star's life cycle. When a massive star exhausts its nuclear fuel, it undergoes a catastrophic collapse, releasing a tremendous amount of energy and ejecting heavy elements into the surrounding medium. Each supernova observed in M51 has provided unique data on the mechanisms of core collapse, the properties of neutron stars and black holes, and the enrichment of the interstellar medium. Beyond the stars, the Whirlpool galaxy reveals the enigmatic role of dark matter in shaping cosmic structures. While the visible mass of the galaxy accounts for its luminous features, it cannot explain the observed rotational velocities of stars in its outer regions. This discrepancy points to the presence of a vast halo of dark matter, an invisible but critical component of the galaxy. By studying the rotational dynamics of M51, astronomers have refined models of dark matter distribution and its influence on galactic evolution. The galactic vortex of NGC 5194 also contributes to our understanding of feedback mechanisms in galaxies. The central black hole, through its accretion activity, generates powerful winds and jets that can influence star formation across the galaxy. This feedback loop, where the energy output of the nucleus regulates the availability of gas for star formation, is a key factor in determining the life cycle of galaxies. Observations of these processes in M51 have helped validate theories about the coevolution of supermassive black holes and their host galaxies. The Whirlpool's companion, sometimes dubbed the stellar companion nexus, plays an equally vital role in shaping the primary galaxy. As it orbits and interacts with NGC 5194, it acts as both a disruptor and a catalyst. The gravitational forces exerted by the smaller galaxy create tidal streams and induce bursts of star formation, while also redistributing angular momentum within the system. This dynamic interplay offers a microcosm of the larger processes at work in galaxy clusters, where interactions between member galaxies drive the evolution of the entire system. On the observational front, the Whirlpool-like entity has been a proving ground for cutting-edge technology. Instruments like the Atacama Large Millimeter/Submillimeter Array, ALMA, have been used to study the cold molecular gas in the galaxy, providing a detailed map of the raw materials available for star formation. Meanwhile, the James Webb Space Telescope promises to unveil even more details about the galaxy's hidden regions, shedding light on its youngest stars and the earliest phases of stellar evolution. The celestial tidal marvel continues to captivate astronomers and the public alike. Its visual appeal, combined with its scientific significance, makes it a cornerstone of modern astrophysics. As our tools and techniques for exploring the cosmos improve, the Whirlpool galaxy will undoubtedly remain a focal point for discovery, offering new insights into the nature of the universe and our place within it. The spiral marvel of Cain's Venatici, often hailed as a galactic masterpiece, remains an enduring focus of cosmic exploration. Its prominent features and ongoing processes make it a living laboratory for unraveling universal mysteries, from the smallest scales of star formation to the vast influence of gravitational forces across millions of light-years. The celestial tidal symphony, as it's also called, is not just a static image of the cosmos but a dynamic and evolving system. The gravitational interplay between the primary galaxy, NGC 5194, and its smaller satellite, NGC 5195, serves as a clear demonstration of how galaxies grow, interact, and transform over cosmic timescales. Current models suggest that the smaller galaxy has passed through the larger one's disk multiple times, leaving behind ripples of star formation, streams of displaced gas, and arcs of stellar populations. Each pass disrupts and reinvigorates the system, triggering phenomena that provide critical insights into galaxy formation and evolution. One of the most scientifically valuable aspects of the grand spiral dynamo is the interplay between its spiral arms and its interstellar medium. These arms are defined by their luminous regions of star formation, where gas clouds collapse under their own gravity to form stars. However, these regions are not evenly distributed, they are influenced by the density waves propagating through the galactic disk. The study of these waves has refined our understanding of how spiral structures are maintained in galaxies and how material is redistributed within them. The stellar collision pair has also become a key source for exploring the complex life cycle of galaxies. Tidal forces from the interaction with its companion have stripped stars and gas from the primary galaxy, creating tidal tails that arc far beyond its visible disk. These features are not only visually stunning but also contain vital information about the mass and composition of the interacting galaxies. Observations of these tidal streams have allowed astronomers to reconstruct the history of the interaction, providing a timeline for when and how the galaxies began their gravitational dance. The cosmic whirlpool engine, as some refer to it, is also a prolific site for stellar death and rebirth. Observations of supernovae within the galaxy's arms have offered invaluable data on the mechanisms of stellar explosions and their role in the cosmic cycle. These events release heavy elements like iron, nickel, and gold into the interstellar medium, enriching it and paving the way for the next generation of stars and planets. Each supernova leaves behind either a neutron star or a black hole, depending on the mass of the progenitor star, contributing to the population of compact objects within the galaxy. In addition to its stellar drama, the galactic nexus of NGC 5194 has become a focal point for studying the role of magnetic fields in shaping galaxies. Radio observations have revealed that magnetic field lines align with the galaxy's spiral arms, acting as invisible scaffolding that guides the movement of charged particles and influences star formation. These findings have implications for understanding the role of magnetism in other spiral galaxies and even in the early stages of galaxy formation in the universe. The whirlpool-like giant has also been instrumental in studying the enigmatic nature of dark matter. By analyzing the rotation curves of the galaxy, astronomers have determined that the visible matter within the galaxy cannot account for its observed gravitational effects. Instead, a massive halo of unseen dark matter surrounds the galaxy, exerting a stabilizing influence on its structure. This discovery has made the whirlpool a cornerstone in the ongoing quest to understand the true nature of dark matter and its role in the cosmos. The galactic stellar forge, as NGC 5194 is sometimes known, is equally valuable for its contributions to the study of cosmic feedback. The supermassive black hole at its core, surrounded by an accretion disk of infalling material, generates powerful outflows of energy. These outflows interact with the surrounding interstellar medium, heating and dispersing gas and regulating star formation within the galaxy. This process, known as feedback, is a critical component of galaxy evolution, and the whirlpool provides a rare opportunity to observe it in action. The interaction between the interstellar symphony and its companion has also reshaped the orbits of stars within the primary galaxy. As the smaller galaxy's gravity pulls on the whirlpool's disk, it creates complex patterns of motion that can be observed using spectroscopic techniques. These patterns offer a unique window into the dynamics of galactic disks and the long-term effects of tidal forces. By studying these motions, astronomers have gained a deeper understanding of how galaxies settle into equilibrium after collisions and mergers. The whirlpool system has also been a proving ground for some of the most advanced observational technologies. Instruments aboard the Hubble Space Telescope have provided high-resolution images that reveal the galaxy's intricate dust lanes, star clusters, and luminous core. Ground-based observatories equipped with adaptive optics have further enhanced our ability to study the galaxy, while radio telescopes like the Very Large Array have mapped the distribution of neutral hydrogen gas, shedding light on the large-scale structure of the system. Looking to the future, the Whirlpool galaxy is poised to reveal even more secrets as new technologies come online. The James Webb Space Telescope, with its unparalleled infrared capabilities, will peer deep into the dust-shrouded regions of the galaxy, uncovering hidden star-forming regions and providing unprecedented detail on its youngest stars. Meanwhile, next-generation radio telescopes like the Square Kilometre Array will map the galaxy's magnetic fields and gas dynamics with unparalleled precision. The celestial maelstrom remains not only a testament to the beauty of the cosmos but also a key to understanding its underlying mechanics. Its intricate structure, dynamic interactions, and rich history make it a natural laboratory for exploring the fundamental principles of astrophysics. As our tools and techniques for studying the universe continue to evolve, the Whirlpool galaxy will undoubtedly remain a centerpiece of scientific discovery, offering new insights into the nature of galaxies and their role in the grand tapestry of the universe. The dynamic spiral of Cain's Venatici, scientifically known as NGC 5194, continues to serve as a cornerstone for cutting-edge astrophysical research. Its wealth of observable phenomena has made it an unparalleled laboratory for investigating galaxy formation, stellar evolution, dark matter dynamics, and even the broader mechanisms governing cosmic structure. The data derived from the Whirlpool galaxy system consistently refine our theoretical models and challenge existing paradigms in galactic astrophysics. One of the most studied aspects of this grand spiral dynamo is its remarkably well-defined spiral arms, which serve as a physical manifestation of density wave theory. Proposed in the mid-20th century, this theory suggests that spiral arms are not fixed structures but rather areas of increased density that move like waves through the galaxy's disk. In this model, stars, gas, and dust flow in and out of the spiral arms, much like cars slowing down and speeding up in a traffic jam. The arms of the galactic whirlpool nexus are active zones of star formation. As the density waves compress interstellar gas clouds, the increased pressure triggers the collapse of these clouds, leading to the birth of new stars. This process is observable in the bright knots of young, massive stars within the arms, which emit intense ultraviolet radiation and ionize surrounding hydrogen gas. These regions, often referred to as H2 regions, glow brightly in optical wavelengths and are key markers of ongoing star formation. Using spectroscopic data from instruments like the Sloan Digital Sky Survey, SDSS, and the Multi-Unit Spectroscopic Explorer, MUSE, astronomers have mapped the velocity fields within these arms. These studies reveal the intricate interplay between gas dynamics, star formation, and feedback from massive stars. The high-resolution data also highlight the role of turbulence and magnetic fields in shaping the star-forming regions, providing new insights into the physical conditions that drive stellar birth in spiral galaxies. The cosmic tidal pair, consisting of NGC 5194 and its companion NGC 5195, exemplifies the dramatic effects of gravitational interactions between galaxies. These tidal forces are responsible for many of the features observed in the Whirlpool galaxy, including its sharp spiral arms and extended tidal tails. The gravitational interaction between the two galaxies has also induced large-scale gas flows within NGC 5194, redistributing material and fueling bursts of star formation. One of the most striking results of this interaction is the creation of a luminous bridge of stars and gas that connects the two galaxies. This structure is a direct consequence of tidal stripping, where gravitational forces from the smaller galaxy pull material from the larger one. Observations of this bridge in multiple wavelengths, including radio, optical, and infrared, have provided critical data on the dynamics of tidal interactions and the role of these processes in galaxy evolution. Hydrodynamic simulations of the stellar collision duo have allowed researchers to reconstruct the history of their interaction. These models suggest that NGC 5195 has passed through the disk of NGC 5194 at least once, with each encounter generating new waves of star formation and reshaping the structure of both galaxies. Such simulations are not only crucial for understanding the specific history of the Whirlpool galaxy but also serve as a template for studying similar interactions in other systems. At the core of the interstellar vortex, a supermassive black hole with a mass estimated to be millions of times that of the Sun dominates the dynamics of the central region. This black hole, surrounded by an accretion disk of infalling material, occasionally flares in bursts of high-energy radiation. These emissions, observed in X-ray and radio wavelengths, classify the nucleus as a low-luminosity active galactic nucleus, AGN. The AGN in NGC 5194 provides a unique opportunity to study the feedback mechanisms that regulate galaxy evolution. As the black hole accretes material, it releases powerful jets and winds that interact with the surrounding interstellar medium. These outflows can heat and disperse gas, suppressing star formation in the central regions of the galaxy. This process, known as AGN feedback, is a key component of galaxy evolution models and helps explain the observed relationships between black hole mass and the properties of their host galaxies. Recent observations using the Chandra X-ray Observatory have revealed intricate structures in the hot gas surrounding the nucleus. These structures, including shock fronts and cavities, are thought to be the result of interactions between the AGN outflows and the surrounding interstellar medium. By studying these features, astronomers are gaining new insights into the role of black holes in shaping their host galaxies. The galactic dynamo nexus is also a prime site for investigating the role of magnetic fields in shaping galactic structure and star formation. Using radio observations, astronomers have mapped the magnetic field lines within the galaxy, which closely follow the spiral arms. These fields play a crucial role in regulating the collapse of gas clouds, influencing both the rate and efficiency of star formation. The alignment of magnetic fields with the spiral arms is thought to result from the interaction between density waves and the galaxy's differential rotation. This process, known as the alpha-omega dynamo, amplifies and organizes the magnetic fields, creating the ordered patterns observed in the Whirlpool galaxy. The study of these fields not only enhances our understanding of M51 but also provides broader insights into the role of magnetism in other galaxies. The rotation curve of the stellar Whirlpool system provides compelling evidence for the existence of dark matter. Observations show that the orbital velocities of stars in the outer regions of the galaxy remain constant, rather than decreasing as would be expected based on the visible mass alone. This discrepancy suggests the presence of a massive dark matter halo that extends far beyond the visible boundaries of the galaxy. By combining optical and radio observations, astronomers have mapped the distribution of dark matter within the Whirlpool galaxy. These studies have refined our understanding of the role of dark matter in shaping the structure and dynamics of galaxies. They also contribute to the broader effort to understand the nature of dark matter, one of the most profound mysteries in modern physics. The luminous spiral pair serves as a microcosm of the processes that drive cosmic evolution. Its well-documented history of interaction, active star formation, and dynamic feedback mechanisms provides a detailed case study for understanding how galaxies grow and change over time. By comparing the Whirlpool galaxy to more distant systems, astronomers can trace the evolutionary pathways of galaxies across cosmic history, from their formation in the early universe to their present-day structures. As observational technology continues to advance, the Whirlpool-like entity will undoubtedly yield even more secrets. Instruments like the James Webb Space Telescope and next-generation radio arrays promise to provide unprecedented detail on its hidden regions, offering new insights into the processes that drive galaxy evolution. Each discovery brings us closer to answering the fundamental questions about the nature of the universe and our place within it. The spiral marvel of the northern skies, a system defined by its vivid, intricate design and profound scientific depth, is a living chronicle of the cosmos, waiting to unveil its secrets to those who study it. Beyond its captivating appearance lies an extraordinary network of physical phenomena and cosmic forces that challenge and refine humanity's understanding of the universe at every level. This stellar system, often romantically described as a cosmic hurricane frozen in time, is more than a grand visual masterpiece. It is a dynamic interaction of gravity, magnetism, and matter, creating a stage where the rules of galactic evolution play out vividly. Every spiral arm, star-forming region, and shock wave in this system is a vital clue to the nature of galaxy formation and the interconnected forces shaping the fabric of the universe. The gravitational bond between the luminous Whirlpool nexus and its satellite galaxy, often called the cosmic intruder, is a phenomenon both violent and beautiful. Their interaction creates gravitational tidal forces so immense that they physically distort the disks of both galaxies, producing long tidal tails and streams of gas that stretch across tens of thousands of light-years. These streams, glowing faintly in infrared light, are thought to carry the raw ingredients for star formation, acting as highways of interstellar matter connecting the two galaxies. The spiral arms of the interstellar dynamo, with their exquisite definition, are sculpted not by chance but by the collision and compression of gas clouds triggered by these tidal forces. The density waves moving through the disk act as catalysts, creating the conditions necessary for massive star formation. These stars, though young and short-lived, release copious amounts of energy and radiation, which then propagate outward, lighting up the spiral arms in ultraviolet and optical wavelengths. This cycle of compression, star formation, and feedback defines the very heartbeat of the galaxy. Recent studies have revealed that these arms are rich not only in stars but also in enigmatic structures such as molecular gas clouds and filaments of interstellar dust. Observations from the Atacama Large Millimeter/Submillimeter Array, ALMA, have identified regions within the arms that are on the verge of collapse, giving astronomers a chance to witness the earliest stages of stellar birth. These discoveries have expanded humanity's understanding of how gas turns into stars, providing critical insights into one of the most fundamental processes in the cosmos. But the galactic Whirlpool pair holds mysteries that go far beyond star formation. Deep within its luminous core lies an engine of incomprehensible power, a supermassive black hole. This behemoth, millions of times the mass of the Sun, exerts a gravitational influence so strong that it shapes the very dynamics of the galaxy. Material falling into this black hole forms an accretion disk, which heats to millions of degrees, producing powerful jets and outbursts of radiation that can be detected across the electromagnetic spectrum. These emissions are not merely fascinating, they are clues to the physics of matter under extreme gravitational forces, revealing processes that cannot be replicated on Earth. The role of the black hole extends beyond its immediate vicinity. Its energy outbursts send shockwaves through the interstellar medium, heating gas clouds and disrupting their collapse into stars. This dual role of creation and destruction makes the nucleus of the Whirlpool entity a focal point for understanding the delicate balance of forces that governs galaxy evolution. By observing this system, scientists are piecing together how black holes influence not only their host galaxies but also the broader cosmic environment. One of the most intriguing features of the cosmic tidal symphony is the faint, ghostly glow of its dark matter halo. This invisible structure, which outweighs the visible galaxy by several times, is inferred from the motion of stars in the galaxy's outer regions. The rotational velocity of these stars defies the expectations set by visible matter alone, suggesting the presence of a vast, unseen mass. This discovery is not unique to the Whirlpool but is a hallmark of nearly all galaxies, making it a cornerstone of modern astrophysics and a gateway to understanding the elusive nature of dark matter. While much of the galaxy's activity is focused on its dense core and active arms, its outer regions tell a quieter but equally compelling story. Here, in the faint periphery of the luminous spiral nexus, ancient stars orbit in near isolation, remnants of an earlier epoch in the galaxy's history. These stars, some of which are globular clusters, serve as living fossils, preserving the chemical signatures of the galaxy's past. By analyzing their light, astronomers can reconstruct the formation history of the galaxy, tracing its evolution back billions of years. The ongoing interaction with the smaller satellite galaxy continues to shape the destiny of this celestial pair. Simulations suggest that the two galaxies are locked in a gravitational embrace that will eventually culminate in their merger, a process that could take hundreds of millions of years. This merger will not be a simple union but a chaotic and transformative event, likely resulting in the formation of an entirely new galaxy type. The tidal forces unleashed during this collision will scatter stars, gas, and dust, while triggering waves of star formation and reshaping the system's structure in ways that are only beginning to be understood. Adding to the intrigue, the grand stellar whirlpool has proven to be a prolific site for supernovae. These stellar explosions, among the most energetic events in the universe, are a natural consequence of the galaxy's intense star formation. Each supernova not only marks the death of a massive star but also enriches the surrounding medium with heavy elements, creating the building blocks for future generations of stars and planets. Observing these events in real time has allowed scientists to refine their models of stellar death and the mechanics of core-collapse supernovae. The more scientists delve into the depths of the galactic maelstrom, the more questions arise. How do its magnetic fields interact with the spiral arms? What role does turbulence in its interstellar medium play in regulating star formation? And how will its eventual merger with its companion reshape its future? These questions drive a relentless pursuit of knowledge, pushing the boundaries of what humanity knows about the universe. As humanity's observational tools grow ever more sophisticated, from the James Webb Space Telescope to ground-based observatories with adaptive optics, the dynamic vortex galaxy will undoubtedly continue to yield its secrets. Each new discovery not only deepens our understanding of this iconic system but also provides a broader context for understanding the universe as a whole. The Whirlpool Galaxy is not just a spectacle, it is a living narrative of cosmic forces, a story of birth, transformation, and eventual rebirth on a scale that defies imagination. And in its glowing arms and luminous core lies the promise of countless more revelations to come. The cosmic maelstrom, as astronomers have come to know it, is far more than a galactic archetype, it is a symphony of forces, an interplay of energy and gravity that operates on a stage so vast that its full drama unfolds over tens of millions of years. Every photon escaping its vibrant spiral arms carries with it the whispers of physical processes that have shaped the universe for billions of years. This intricate galactic tapestry serves as both a map and a mirror, reflecting the universal laws of nature. At the heart of this stellar whirlpool, the supermassive black hole acts as both creator and destroyer. Its influence extends far beyond the core, shaping not just the dynamics of nearby stars but also regulating star formation across the galaxy. When gas spirals into the black hole's accretion disk, it heats up to extraordinary temperatures, emitting intense X-rays and sometimes forming powerful relativistic jets. These jets, moving at nearly the speed of light, can punch through the galaxy's interstellar medium, creating shock waves that compress gas clouds or, conversely, blow them apart. This mechanism, known as feedback, is a key process in regulating galaxy evolution, and the whirlpool's active nucleus is a pristine laboratory for studying it. Observations in the X-ray spectrum using instruments like Chandra have revealed fascinating details about this activity. Hot gas in the nucleus of the interstellar vortex glows in X-rays, outlining the regions where energy from the black hole is interacting with its surroundings. These high-energy interactions are not limited to the nucleus alone. Fainter X-ray emissions trace supernova remnants scattered throughout the spiral arms, powerful evidence of the galaxy's prolific star formation and the violent deaths of massive stars. These remnants also emit neutrinos and cosmic rays, whose detection on Earth provides a direct link between this galaxy and our own. The luminous dynamo also showcases an abundance of molecular gas, the raw material for star formation. Using radio telescopes like ALMA, scientists have mapped vast reservoirs of cold molecular hydrogen in its arms. These cold, dense regions are peppered with massive, turbulent gas clouds that are collapsing to form stars. Within these clouds, gravitational instabilities trigger the formation of stellar clusters, which then light up the arms in ultraviolet and visible wavelengths. But the process is not straightforward. The interplay between gravity, turbulence, magnetic fields, and radiation pressure creates a complex environment where only a fraction of the gas forms stars. Magnetic fields, which have been mapped using polarized radio waves, thread through the spiral tidal nexus, acting as both an inhibitor and a guide for gas flows. These fields channel charged particles along their lines, influencing the motion of gas and dust and shaping the birthplaces of stars. The alignment of magnetic fields with the galaxy's spiral arms is a striking example of the cosmic order arising from seemingly chaotic processes. As if the dynamism of its spiral arms weren't enough, the galactic tidal symphony reveals yet another layer of intrigue: the presence of interstellar shocks caused by the passage of its satellite galaxy, NGC 5195. When this smaller galaxy passed through the disk of the whirlpool, it induced massive waves of compression, heating gas clouds and triggering bursts of star formation. These shock fronts are visible as arcs of ionized gas glowing in H-alpha light, a testament to the ongoing impact of this gravitational interplay. These waves of activity are rippling outward, reshaping the structure and composition of the galaxy's outer disk. The gravitational interaction has also created the iconic bridge of material that connects the Whirlpool system to its smaller companion. This bridge, made of stars and interstellar gas, is a physical testament to the power of tidal forces. Spectroscopic studies of the bridge reveal peculiar velocity profiles, with gas moving in highly complex patterns. These measurements confirm that material is actively being transferred between the two galaxies, fueling star formation in both systems and altering their evolutionary trajectories. In addition to being a stellar nursery, the celestial maelstrom is a galactic forge where heavier elements are produced and dispersed. Every massive star that forms in the spiral arms eventually ends its life in a spectacular supernova, releasing elements such as carbon, oxygen, and iron into the surrounding medium. These enriched gas clouds later coalesce into new stars and planets, embedding the fingerprints of previous generations into future ones. The Whirlpool galaxy is, in essence, a self-sustaining cosmic engine, perpetually recycling and renewing itself. Dark matter plays a pivotal role in maintaining this engine. The rotational curve of the spiral vortex defies classical Newtonian expectations, with stars at the outer edges moving much faster than predicted by the visible mass alone. This discrepancy is attributed to a massive halo of dark matter that envelopes the galaxy, extending well beyond its visible edge. The presence of this unseen mass not only stabilizes the spiral structure but also influences the dynamics of tidal interactions with its companion galaxy. By studying the distribution and influence of dark matter in the Whirlpool galaxy, astronomers are refining their understanding of this mysterious component of the universe, which constitutes nearly 27% of its total mass energy content. The stellar collision nexus also serves as a laboratory for studying cosmic dust, an often overlooked but critical component of the interstellar medium. Dust grains, composed of silicates, carbon, and other heavy elements, are formed in the atmospheres of dying stars and during supernova explosions. These tiny particles absorb and scatter light, making them both a challenge and a boon for observational astronomy. In the Whirlpool, dust lanes weave through the spiral arms, casting shadows and creating stark contrasts that highlight the galaxy's structure. Infrared observations from the Spitzer Space Telescope and the James Webb Space Telescope have illuminated these dust-rich regions, revealing the hidden star-forming factories buried within. On the largest scales, the dynamic spiral entity interacts not only with its companion but also with the surrounding intergalactic medium. Faint, diffuse emissions of gas have been detected beyond its visible disk, hinting at interactions with the larger cosmic web of matter that connects galaxies across vast distances. These faint emissions, traced through neutral hydrogen studies, reveal that the Whirlpool galaxy is not an isolated system but part of a much larger, interconnected structure. This cosmic web is the scaffolding of the universe, and the Whirlpool galaxy offers a glimpse into how galaxies draw material from these intergalactic reservoirs. As research continues, the Whirlpool-like giant serves as a beacon of discovery, challenging astronomers to push the boundaries of technology and theory. It is a system that operates on timescales so vast and scales so immense that it humbles the human imagination. Yet, within its swirling arms and luminous core, it carries the answers to some of the most profound questions about the nature of the cosmos and our place within it. Every photon, every molecule of gas, Every burst of energy from a dying star adds to the story of a galaxy that is as much a laboratory as it is a masterpiece of the universe. Let me know if you'd like me to further expand specific sections or explore additional cosmic phenomena. The spiral masterpiece of Cain's Venatici, often heralded as one of the most studied galactic systems in our cosmic neighborhood, continues to reveal mysteries that push the boundaries of astrophysics. Its dynamic environment, driven by an intricate interplay of gravity, radiation, magnetism, and dark matter, offers an unparalleled opportunity to study phenomena that are otherwise impossible to replicate on Earth. At the forefront of modern research lies the question of galactic interaction dynamics. The Whirlpool Galaxy, or Interstellar Collision Laboratory, has become a key observational target for understanding how galaxies evolve through interactions. The ongoing gravitational tug-of-war between NGC 5194 and its smaller companion, NGC 5195, serves as a natural experiment, offering astronomers a snapshot of a process that unfolds over hundreds of millions of years. Advanced hydrodynamic simulations have been employed to model the tidal forces sculpting the Whirlpool Galaxy's spiral arms and the extended gas bridges connecting the two galaxies. These simulations, powered by some of the world's most sophisticated supercomputers, reveal how repeated passes of NGC 5195 through the disk of NGC 5194 induce waves of star formation and redistribute mass across the system. Each pass acts like a stone dropped in a cosmic pond, generating ripples of compression that propagate outward through the galactic disk. These ripples trigger starbursts, intense periods of star formation that light up the galaxy in ultraviolet and infrared wavelengths. The galactic forge has become an essential focus for understanding these starbursts. Observations using the Hubble Space Telescope and the James Webb Space Telescope have identified compact clusters of young stars nestled within the spiral arms. These clusters are often surrounded by cocoons of ionized gas, glowing brightly in H-alpha light. By studying these regions, researchers have uncovered the role of turbulence in regulating star formation. Turbulence, driven by gravitational interactions, creates pockets of high-density gas within the arms, which collapse under their own gravity to form stars. The ongoing interaction has also exposed a remarkable phenomenon known as shock-induced star formation. As the companion galaxy passes through the Whirlpool's disk, it generates shock fronts, regions where gas is compressed and heated by the collision of massive interstellar flows. These shock fronts, observed in the far-infrared and millimeter wavelengths, are prolific sites for star formation. The conditions within these regions are so extreme that they provide a glimpse into the processes that likely occurred during the universe's early epochs when galaxy collisions were more frequent. The cosmic dynamo also offers a rare opportunity to study the role of magnetic fields in shaping galactic structure. Using advanced radio telescopes like the Very Large Array and the Square Kilometre Array, SKA, astronomers have mapped the magnetic field lines threading through the galaxy's spiral arms. These fields, amplified by the galaxy's rotation and density waves, guide the movement of charged particles and influence the dynamics of interstellar gas. Magnetic fields are thought to play a critical role in the collapse of molecular clouds, acting as both a brake and a catalyst for star formation. Adding another layer of complexity, the stellar collision symphony is an active participant in the cosmic cycle of matter and energy. Its spiral arms are rich in dust and molecular gas, the raw materials for star formation, but they are also constantly being replenished by the deaths of massive stars. Supernovae, which occur frequently in this starbursting galaxy, release heavy elements into the interstellar medium, enriching it with the building blocks for planets, life, and future generations of stars. Each supernova is a localized explosion of energy, creating shockwaves that ripple through the surrounding medium, compressing gas and seeding the next wave of star formation. The study of supernova remnants in the whirlpool has become a critical area of astrophysical research. Instruments like Chandra and XMM Newton have detected the faint X-ray glow of hot gas in these remnants, providing a window into the late stages of stellar evolution. These observations are complemented by neutrino detections on Earth, which offer a rare glimpse into the processes occurring in the cores of dying stars. The Whirlpool galaxy has thus become a key player in the global effort to understand core-collapse supernovae, which are among the most powerful events in the universe. The gravitational tidal theater also serves as a testing ground for theories of dark matter distribution. By analyzing the motions of stars and gas in the galaxy's outer regions, astronomers have reconstructed the shape and extent of its dark matter halo. These studies reveal that the dark matter in NGC 5194 forms an enormous, invisible halo that extends far beyond the visible disk, encompassing both the primary galaxy and its satellite. This halo not only stabilizes the spiral arms but also influences the dynamics of the interaction with NGC 5195. By comparing these findings to simulations of galaxy formation, researchers are refining their understanding of how dark matter drives the growth and evolution of galaxies. On the larger scale, the luminous whirlpool nexus offers insights into the role of galaxies within the cosmic web, the vast network of dark matter and gas that connects galaxies across the universe. Neutral hydrogen observations using radio telescopes have revealed faint streams of gas extending from the whirlpool into the intergalactic medium, hinting at ongoing interactions with the larger cosmic environment. These gas streams may represent the inflow of material from the cosmic web into the galaxy, providing the fuel for future star formation. Perhaps one of the most tantalizing mysteries of the dynamic spiral entity is its eventual fate. The interaction with NGC 5195 is a prelude to an inevitable merger, a process that will transform the Whirlpool galaxy into an entirely new structure. Simulations predict that this merger will destroy the elegant spiral pattern, replacing it with a chaotic mix of stars and gas. Over time, the system will settle into a more stable elliptical or lenticular form. While this transformation will take hundreds of millions of years to complete, it offers a glimpse into the ultimate destiny of many spiral galaxies, including our own Milky Way, which is on a collision course with the Andromeda Galaxy. As telescopes grow ever more powerful and theoretical models become increasingly sophisticated, the stellar tidal giant will undoubtedly continue to yield new discoveries. Its dynamic environment, rich in observable phenomena, makes it a cornerstone of modern astrophysics and a symbol of the beauty and complexity of the cosmos. Each new revelation from the Whirlpool galaxy brings humanity one step closer to unraveling the ultimate mysteries of the universe, reminding us that, even in the vastness of space, the laws of physics remain beautifully consistent and endlessly fascinating. Let me know if you'd like me to go deeper into specific aspects or expand further on recent research. The luminous spiral forge, a stellar laboratory unlike any other, continues to intrigue scientists with its dynamic processes and relentless activity. Its seemingly tranquil beauty hides a cauldron of physical forces that drive the evolution of galaxies, create and destroy stars, and sculpt the universe on both local and cosmic scales. Every new observation of this celestial masterpiece peels back another layer of its complexity, offering deeper insights into phenomena that have shaped the cosmos for billions of years. One of the most compelling ongoing investigations into the interstellar vortex focuses on its remarkable ability to sustain starburst activity over extended periods. While star formation is common in spiral galaxies, the whirlpool is unique in its high efficiency at converting gas into stars, particularly in the dense regions of its spiral arms. Detailed spectroscopic studies have revealed the chemical composition of these regions, showing an abundance of heavier elements, products of countless previous generations of stars. This enrichment accelerates the process of star formation by cooling the gas more efficiently, allowing it to collapse into stars at a faster rate. What sets the cosmic dynamo apart is the extraordinary diversity of stellar populations within it. The galaxy's arms are home to massive, hot, young stars that shine brightly in ultraviolet light, while its outskirts harbor older, cooler stars that trace the galaxy's ancient history. This juxtaposition allows astronomers to study the full spectrum of stellar evolution in a single system. By comparing the properties of these different populations, researchers can reconstruct the history of star formation in the galaxy and understand how its interactions with NGC 5195 have influenced its development. The tidal collision duo also serves as a natural laboratory for investigating the behavior of interstellar dust, an essential but often overlooked component of galaxies. Dust grains, though tiny, play a critical role in the life cycle of stars and planets. They absorb ultraviolet and visible light, re-emitting it as infrared radiation, which has been captured in exquisite detail by the Spitzer Space Telescope and, more recently, the James Webb Space Telescope. These observations reveal intricate patterns of dust lanes weaving through the spiral arms, often outlining regions of intense star formation. The dust also provides the raw material for the formation of planets, making the whirlpool a key system for understanding the origins of planetary systems like our own. A particularly exciting avenue of research in the dynamic spiral nexus involves the study of stellar feedback mechanisms. Massive stars, while short-lived, profoundly influence their surroundings through intense radiation, stellar winds, and eventual supernova explosions. This feedback injects energy into the interstellar medium, creating shockwaves that compress gas clouds and trigger new waves of star formation. However, it can also have the opposite effect, dispersing gas and quenching star formation in certain regions. Understanding this delicate balance is crucial for unraveling the processes that govern galaxy evolution, and the whirlpool provides a vivid example of how these mechanisms play out in real time. Meanwhile, the Galactic Gravitational Laboratory continues to illuminate the enigmatic nature of dark matter, which is thought to make up the vast majority of the galaxy's mass. The rotational velocities of stars in the whirlpool's outer regions remain constant, defying the predictions of Newtonian physics based solely on visible matter. This discrepancy points to the presence of an extensive dark matter halo that stabilizes the galaxy's structure and drives its interactions with its companion. By studying the distribution of dark matter in this system, astronomers are gaining critical insights into its role in shaping the large-scale structure of the universe. The celestial whirlpool theater is also a prime target for investigations into galactic magnetic fields, which are notoriously difficult to study but are increasingly recognized as fundamental to the evolution of galaxies. The magnetic fields in the whirlpool, mapped using polarized radio observations, show a remarkable alignment with its spiral arms. These fields are thought to amplify and organize themselves through the galaxy's rotation and density wave patterns. They influence the motion of charged particles, guide the flow of gas, and even affect the collapse of molecular clouds into stars. The study of these fields in the whirlpool has opened a new frontier in astrophysics, linking small-scale processes like star formation to the large-scale dynamics of galaxies. The tidal bridge system connecting NGC 5194 and NGC 5195 is another area of intense study. This luminous structure, composed of stars, gas, and dust, is a direct result of the gravitational interaction between the two galaxies. Detailed spectroscopic analysis has revealed the velocities of gas within the bridge, showing complex motions that reflect the tidal forces at work. These interactions are not merely destructive, they also create opportunities for new star formation. The bridge itself contains regions of active star formation, illuminated by clusters of young, massive stars that have recently formed from the compressed gas.